Now let's discuss the BJT high frequency model. Before we do that, let's take a look at our motivation for studying the BJT frequency response. On the right of your screen, you can see a sketch of gain of the common emitter amplifier versus the frequency. We are not going to go into too much detail into this because we have already covered this topic in the MOSFET module. A link is given in the instructor's notes and you can go and see this topic in more detail over there. What we are going to briefly remark here is that, as evident from this graph, the gain of the BJT amplifier does not remain constant for all frequencies. It falls off after FH and before FL. However, in our derivations, we have been assuming, for the sake of simplicity, that the gain is independent of frequency, but it is not. So we have to analyze the circuit and find FH and FL. By finding, I mean find an expression for them so that we know which quantities control them, and thereby if we change them, we control FH and FL. The reason behind controlling it is that we want our amplifier to operate in the midband. Here, the gain is almost constant. When we are taking an AC signal, it may have a variety of frequencies. All of them need to be amplified by the same amount, otherwise distortion will occur. So, we design our amplifier in such a way that the concerned frequencies coincide with something called the amplifier's bandwidth. In this way, the amplitudes associated with all these frequencies are going to be amplified equally. And now let us look at the BJT high frequency equivalent circuit model that we are going to be employing in our analysis. Here we are, and let me explain to you one by one what these quantities mean. First of all, look at two capacitances, C mu and C pi. This is the collector base junction capacitance. The reason we are studying it and not ignoring it is because at high frequencies, this causes the drain to fall off. Its partner in crime is C pi. This is basically a sum of two capacitances, CDE and CJE. CDE is the base charging or diffusion capacitance, and CJE is the base emitter junction capacitance. Their values are fixed and will be given to you when you are asked to design. Rx is the model resistance, not a resistor, of silicon material between base and B dash. B dash is an imaginary terminal. The reason Rx is included is that at high frequencies, it can accurately model resistive effects between these two terminals. Now, with that out of our way, let's start our high frequency response of the BJT.